Hello class, let's learn how to read Logtable. अरे हे बघा हे दिवसाचा लॉग टेबलवरती लिहितात. अब इसको तो लॉग टेबल सिखाना ही पड़ेगा. Hello. This is Dr. Sheode from Learners Academy, also called LearnAc. In this video, we are going to learn about how to read Logtable, because in board exams, calculators are not allowed. And so the ability to solve the numericals using Logtables is extremely important. So let's start. So let's start with some fundamental ideas and the laws that you might have learned in school. Let's start. A into A into A into A dot n times is equal to A raised to n. Okay, I'm going to refer the book so that I don't miss any of the points that I want to highlight. A raised to minus n is equal to 1 upon A raised to n. Of course, A not equal to 0. A raised to 0 is equal to 1. Of course, A not equal to 0. And you know that nth root of A can be written as A raised to 1 by n. Alright? And A raised to P by Q is actually A raised to P bracket raised to 1 by Q. Of course, Q got to be greater than 0. Now, these are the ideas that you have learned in school. Let's revise very quickly the laws of indices, right? You know, A raised to m into A raised to n is A raised to m plus n. A raised to m bracket raised to n is A raised to mn, right? And A into b bracket raised to n is equal to A raised to n into b raised to n, right? And A raised to m upon A raised to n is A raised to m minus n, right? And A upon b bracket raised to n is equal to A raised to n upon b raised to n, b not equal to 0. Before we even start learning how to read log tables, let us try to understand the basic idea behind the development of log tables. How the log tables are going to make our lives easy when it comes to multiplication and division. You know what? They're just going to convert complex multiplication and division into simple ideas of addition and subtraction. And mind you, addition and subtraction are far easier to do than complex multiplication and division. So let's start. Let's take an example. Okay, have a look at this table. If you observe the row consisting set A, these are just the numbers, and if you see set B and if you observe carefully, you'll find that set B contains exponents of 2. Thus 2 raised to 1 is 2, 2 raised to 2 is 4, 2 raised to 3 is 8, and so on and so forth. Suppose you have to multiply two numbers in the set A, say for example 16 into 256. Locate the exponent corresponding to 16 and 256. They are 4 and 8 respectively, as you can see. Add these exponents, that is 4 plus 8 is equal to 12. Then look for a number in A corresponding to exponent 12. It is 4096, and therefore 16 into 256 is equal to 4096. Note, you have used addition to calculate a product. Is that not a magic? This can be understood if you recall that using first law of indices. If you remember, A raised to m into A raised to n is A raised to m plus n. So when you do 16 into 256, what you essentially are doing is 2 raised to 4 into 2 raised to 8 is equal to 2 raised to 12, which is 4096. Thus, a multiplication has been converted into a simple idea of addition, and you were able to get the answer. And this is what Logtable is all about. Now let's see the magic working for division. Now suppose you have to divide 1024 by 8. The corresponding exponents of 2 are 10 and 3 respectively, as you can see from the table. Subtract the exponent, that is 10 minus 3, which is equal to 7. The number in A corresponding to exponent 7 is 128, and therefore 1024 divided by 8 is 128. Magic again. Note, what have you used? A raised to m upon a raised to n is a raised to m minus n. So 1024 upon 8 is actually equal to 2 raised to 10 upon 2 raised to 3, which is equal to 2 raised to 10 minus 3, which is 2 raised to 7, which is 128. So now let's learn what exactly we mean by the term finding a logarithm. Let's understand the basic idea of logarithm. Now let me explain how logarithm is actually written as. Logarithm in short will be always written as log, L-O-G. Okay? Let's take this example. 10 raised to 2 is equal to 100. And this is written in exponential form, as you can see on the screen. We shall write this statement as log of 100 to the base 10 is equal to 2. What this means is, now 10 is base here and 2 is the exponent of 10. And if you remember, 10 raised to 2 was 100. So 10 raised to 2 is equal to 100 was written in modified form as log of 100 to the base 10 is equal to 2. So what logarithm essentially means is the exponent of 10. Let's take few more examples. For example, 10 raised to 3 is equal to 1000. This can be written as log of 1000 to the base 10 is equal to 3. 10 raised to 4 is equal to 10,000. This can be written as log of 10,000 to the base 10 is equal to 4. Now note here, I am using the term log of 10,000 to the base 10 is equal to 4. This means that 10 is base and 4 is index. So 10 raised to 4 is going to become 10,000. This means that when you are finding logarithm, what you are actually doing is finding the exponent or index of 10. We can have other examples as well. For example, 2 raised to 3 is equal to 8 can be written as log of 8 to the base 2 is equal to 3. Now note here, the base has changed to 2. One more example. 2 raised to 6 is equal to 64 can be written as log of 64 to the base 2 is equal to 6. So here base is 2 and the index is 6. So essentially, when you're finding a logarithm, what you're doing is actually finding the exponent of a base. बहुत पका दिया यार. Before we proceed further, let me tell you some interesting things about Logtable. Let's travel back in time. चलो भूतकाल में जाते हैं. If you remember, the log examples that I discussed were to the base 10. But before these log tables arrived, the actual log tables were to the base e. They were called natural logarithm. The value of e is 2.718. And these log tables were developed by John Napier of Manchester. He was a Scottish landowner and he was a known mathematician, physicist and astronomer. Later on, there was another fellow by the name Henry Briggs who was an English mathematician, and he changed the base from e to 10. The log tables developed by Henry Briggs are called common log tables or Briggsian log tables, and the tables which we use are the common log tables developed by Henry Briggs. Let's learn the basic laws of logarithm. Log of mn to the base b is log m to the base b plus log n to the base b. Now note down, b is base and b is not equal to 1. The second law is log of m by n to the base b is log m to the base b minus log n to the base b. Okay. The third law is log of m raised to n to the base b is n log m to the base b. And the fourth one, what is famously called the change of base rule, is log of m to the base b is equal to log of m to the base c by log of b to the base c. So let us now learn how to find logarithm of a positive real number, say x. So when we want to find out logarithm of a positive real number x, then remember that it is going to consist of two parts. First, characteristic, and second, mantissa. Now the characteristic could be found out orally, and I'll tell you the tricks to find out characteristic. It is the mantissa, which is a non-negative number which we will find using the logarithmic tables. Let's learn the method of finding characteristic by inspection, or you might want to call it oral. To find the characteristic of a number, we consider two groups. One, number greater than 1 and number less than 1. Let's try to find out characteristic of a number greater than 1. Let's take an example. Suppose we have a number 529. What you do is you express this number in decimal form, in the sense you write it as 529.0. The trick is count the number of digits on the left side of decimal. Here the number of digits on the left side of decimal are 3. 1, 2, 3. Subtract 1 from it, which is equal to 2. Thus 2 is the characteristic of the number 529. Let's take another example. 25.29. The number of digits on the left side of decimal are 2. So the characteristic is 2 minus 1, which is equal to 1. Let's take one more example. 5.29. The number of digits on the left side of decimal is 1, and therefore the characteristic is 1 minus 1, which is equal to 0. Thus, as a general rule, we can say count the number of digits on the left of the decimal point of a given number. Suppose it is x, then the characteristic of that number is x minus 1. Let's try to find out characteristic of a positive number less than 1. Here the rule is count the number of zeros appearing immediately after the decimal point and before the first non-zero digit in the decimal form of number. Suppose it is z, then the characteristic is z plus 1 and is denoted by z plus 1 bar. Let's take example. Suppose we have example 0.345. The number of zeros after the decimal point is 0, and so according to the rule 0 plus 1 is equal to 1 bar is the characteristic of this number. Let's take one more example. 0.03908. The number of zeros after the decimal point is 1, and so therefore the characteristic is 1 plus 1, which is equal to 2. 2 bar is the characteristic of this number. Let's take one more example. 0.000932. The number of zeros after the decimal point is 3, and so therefore the characteristic is 3 plus 1 bar, which is equal to bar 4. Thus characteristic can be found out using inspection. Now let us learn how to find mantissa. As I told you, mantissa may be found out using common logarithms. This is how the common logarithm tables look like. We have to find mantissa part of logarithm of a number from the logarithm tables. As you can see, the logarithm table consists of rows and columns. Rows begin with numbers 10, 11, 12 up to 99, and there are 10 columns with headings 0, 1, 2 up to 9. After these columns, there are columns with headings 1, 2, 3, 4 up to 9. These are known as differences or mean differences. Part of the common logarithm tables is shown here on the screen now. The complete logarithm tables will be available to you in the section of this video. Note that mantissa for 4-digit number can be found from common logarithm tables. While finding mantissa, remember we have to ignore the decimal point. The following example will illustrate the use of logarithm table for finding the mantissa. Let us try to find out mantissa of the number 431.5. As I said, ignore the decimal point, and so the number becomes 4315. Consider the first two digits, that is 43. Look at the row starting with 43. Since the next digit in 4315 is 1, find the number in this row in the column headed by 1. Here you will find 6345 in the table. Then find the number in the same row under the column 5 of mean differences, 5 being the next last digit in 4315. The difference is 5. Add the difference 5 to 6345. Thus 6345 plus difference 5 is equal to 6350, and so the mantissa of 4315 is 0.6350. Now let's try to find out mantissa of the number 0.008576. As I said before, ignore the decimal point, and then the number is just 8576. Reading the row starting with 85 under the column with heading 7, 7 being the next digit with after 85, you will find 9330. Next digit after 7 being 6. Find in the same row under the column 6 of the mean difference. The difference is 3. Adding the difference 3 to 9330 becomes 9330 plus 3 is equal to 9333. Hence mantissa for 8576 is 0.9333. Now let's try to find out the logarithm of number 431.5. As we have seen, log of x is actually equal to characteristic of x plus mantissa of x. And we have seen that characteristic of 431.5 is 2 and mantissa of 431.5 is 0.6350. Thus, log of 431.5 is equal to 2 plus 0.6350, which is 2.6350. Similarly, if we try to find out logarithm of 0.008576, then logarithm of 0.008576 is equal to characteristic plus mantissa. As we have seen, the number of zeros after the decimal point are 2, and therefore 2 plus 1, that is bar 3 is the characteristic, and 0.9333 is the mantissa which we have found using the logarithmic tables. And therefore, the logarithm of 0.008576 is bar 3.9333. Here, note that bar 3 is a negative number and 0.9333, which is a mantissa, which is a non-negative number. समझा क्या? अबे सारे सो रहे हैं, अभी तो antilog सीखना है. When we found out logarithms, what we actually did was finding out the powers of 10. Remember, we are using common logarithms. Do you remember this table we saw right in the beginning of the video? Now in this table, we have found out actually what is called set B numbers. Now we want to go from set B numbers back to set A, that is the final result. That process of going from set B to set A is what we call finding antilogarithm. So now we will learn the trick to find out antilogarithm. Let's start. Let us find antilog of, say, a number 2.6358. For this, we will need the antilog table. And this is how the antilog table looks like. Here, we have to find the number whose log is equal to 2.6358. So, if the required number is y, then log y is equal to 2.6358, which is equal to 2 plus 0.6358. But recall, log y is equal to characteristic of y plus mantissa of y. Hence, characteristic of y is 2 and mantissa is equal to 0.6358. Let's take step number 1. First, consider just the mantissa part, that is 0.6358. In the antilog table, the entry in the row beginning with 0.63 and under the column headed by 5 is 4315. Since the next digit in 0.6358 is 8, find the number in the same row and in the difference column with heading 8. This number is 8. Add the 2, that is 4315 plus 8, which is 4323. Great. Now step number 2. Since the characteristic of number is 2, the number of digits before the decimal point must be 3. Hence, the required number is 432.3. Let's take one more example. Antilog of bar 2.5428. Forget about bar 2. Consider only the mantissa part 0.5428. The entry in antilog table in the row beginning with 0.54 under the column headed by 2 is 3483. In the difference column headed by 8 in the same row you find number 6. Add the 2, that is 3483 plus 6 is 3489. Since the characteristic is bar 2, that is the number of zeros after the decimal point is 1. Hence the required number is equal to 0.03489. So now let's take two examples, one of multiplication and one of division. So the idea is engraved in your mind and you practice more and more. Remember, it is only practice and practice that is going to make you perfect in reading the log table and solving the numericals effectively. Let's take an example. 26.57 multiplied by 18.39. Let us try to find out the answer to this complex multiplication using log. Recall that log of m into n is log of m plus log of n. So we will have to find out log of 26.57 and log of 18.39 separately. So log of 26.57, if you use the log table now and use the trick that I have taught you, comes out to be 1.4243. Remember, here you found out characteristic as well as mantissa. Log of 18.39 turns out to be 1.2646. That means now you have ended up finding the powers of 10. Add these powers of 10 because remember log of m into n is log n plus log n. So 1.4243 plus 1.2646 is 2.6889. Remember, now we have to find out antilog of 2.6889. Go to the antilog table and find out antilog of 2.6889. Turns out to be 488.5. Thus, we have arrived back in set A, if you remember. Thus, 26.57 multiplied by 18.39 is 488.5. Let's take second example. 53.86 divided by 9.035. Now, remember that log of m upon n is log m minus log n. Thus, we will have to find out log of 53.86 and log of 9.035 separately. Whatever I have taught you, try to find out log of 53.86 and log of 9.035. They turn out to be 1.7313 and 0.9559 respectively. Subtract them. They turns out to be 0.7754. Remember, after having found out log, we have to find antilog to get to the final answer. So antilog of 0.7754 is 5.962. And so the answer of 53.86 divided by 9.035 is 5.962. Arey झेपलं का? I hope you had fun learning how to read Logtable and antilog. You might feel that you've understood, but remember, unless and until you practice more, you're not going to master the log tables. In boards, calculators are not allowed, so you will have to use log tables only to solve complex numericals. You can start any time, but finish it like a star by practicing more and more. If you liked it, do share with your friends. Thank you.